Okay.
Awesome.
Yeah, I thought it was gonna be all like cool, and as the moment they walked in, I figured it out. But
Not today.
I guess I'm not a Jedi.
No.
I was telling you about Boy, right?
Yeah.
Yeah, I'm gonna start making a retractable one.
Nice.
So I have a question for you.
Yeah.
If you have a lot of little voltages, can you add those up and make
Yeah.
a big one?
So yeah, put it in series.
Put it in series?
So where the positive of one feeds into the negative side of the other. If you have it reversed, then it cancel out. But if you had them, so like on the batteries, you'll see the positive side of the battery touches the negative side of the next battery. So that's what you want to do with yours.
So I need to like generate electricity and charge the battery.
Mhm.
For the battery, if it's more charged, flow.
Use a diode.
Is it
Yeah.
Does that make it just flow one way?
Yeah.
Gotcha.
Yeah, and that can be you could use an LED battery, or not an LED battery, an LED, just a light emitting diode. So that way when the light turns on, it's actually conducting. Or if it's off, you know your battery's charged.
I wonder is actually, so Americans would use it for like just entertainment. But what I want to expand on is like maybe I call them third world countries, but it's really like fourth world countries.
Yeah.
Because a lot of third world countries have electricity and light and stuff.
Mhm.
But, you could basically press a button and it would turn into a flashlight.
Oh, that would be cool.
And then you spin it. So
Yeah.
like kids could be spinning it during the day.
Hopefully we have some folks logged on.
Yep, we got a few.
We have the YouTube live session going.
Yep, we're on.
Okay, folks, it's about that time. I was kind of hoping for more folks in class today, but I'll take what I can get. We're a little bit behind because the electricity activity always slows me down. Talking about electricity, I've drawn little pictures up here for each of the circuits that we explored during our activity. Either one light bulb, two light bulbs, or three light bulbs in series connected to a battery. And the symbols we often use to denote this, because this takes a while to draw little light bulbs and all that, and I'm not very good artist, but what's the convention is to instead of drawing a little light bulb, draw a jaggedy line. That's the symbol for a resistor, because that's essentially what's going on here. These provide electrical resistance to the flow of current. And so for a single light bulb and a battery, we draw basically two parallel lines, one longer, one shorter, to denote a battery or a voltage source. And so our circuit will basically involve a battery, some voltage, and a light bulb over here we labeled R for resistance. And then we've got electrical current going through it. And none of the experiments we did could imply which direction the current flowed, but we could tell that it's always flowing in one direction, either clockwise or counterclockwise. And I mentioned also that Ben Franklin was the first to realize through his experiments that when we separate charge, we're only separating one kind of charge, and the other charge is just the absence of what's been separated. And he had a 50-50 shot, and he blew it. He said, okay, we'll arbitrarily say it's the positive charge. And then when we talk about the flow of electricity, we're going to be talking about the flow of positive charge. And so if you've got a positive end of a battery, we're going to have current going from that end to the other. And this is by the convention that current is the flow of positive charge. Now we know that what's actually happening is electrons are going the other direction. So what we call the electrical current is actually opposite to the actual flow of electrical charge, which we know now to be the other direction. And it wasn't until we learned a lot more about magnetism and identified what particle is the charge carrier did we actually realize which direction charges are actually flowing in a circuit. So it wasn't until the late 1800s, early 1900s, that we really, actually late 1800s, we got a nail on exactly what charge is going which direction. But our convention, even electricity now, is to look at the motion of positive charge. And when we had two light bulbs in series, we write this as one resistor pretty much after another. And this would be equivalent to a circuit like this, but where the resistance is 2R instead of R. So if the resistances were, say, 10 ohms, a 10 ohm resistor followed by another 10 ohm resistor would be equivalent to having a single 20 ohm resistor. And with 3 light bulbs, we draw that as 3 resistors. And we would have the same current everywhere in this circuit. It would just be less than what we had earlier. And if we want to know the current across any resistor, this is where we apply Ohm's law. In that we look at the current flowing through this resistor. Well, multiply that by its resistance will give us the voltage drop across this resistor, with the idea that current is the same throughout the circuit, but what is essentially being diminished with each circuit element, like or each resistance, is the voltage. And voltage is like a push. Hewitt uses an illustration to talk about like water flowing through a pipe, and the voltage is like the pressure in the pipe. It's not the best analogy, but it works okay. And you can think of resistances are places in the pipe where there's like gravel that would tend to impede the flow of water, which is like the flow of electricity. And so in a pipe like this, if we're trying to push using a pump to push water through a pipe where we have 3 sections filled with gravel, we'd see a drop in pressure after each section where we have the gravel. And so that's kind of what's being diminished in the circuit is this voltage. So if the resistors were, say, 10 ohms each, and let's say I had a 30 volt power supply, well, the total resistance is then 30 ohms with a voltage of 30 volts. That means our current is going to be 1 amp total. But there'll be a drop of equal drops across each resistor. So we have a 10 volt drop across this resistor, a 10 volt drop across this resistor, and a 10 volt drop across this resistor. So the voltage drops for equal resistances are going to be equivalent. An example that I thought would be worth mentioning, talking about power, is say we've got a 40 watt light bulb. Are these 40 watts? Yes, these are 40 watt light bulbs I have here. And Interesting. The way I have it here is this is kind of like the circuit that you had in class. These are 40-watt light bulbs, and the current goes through each light bulb and then back. And if I flame the switch, well, let's, I'll do that later. So this is kind of what we saw in class. But if we had a single 40-watt light bulb, the question is what's its resistance? And the question, here's a question for folks. If we have a 40-watt light bulb, what voltage do we put across that light bulb? What do we have in household wiring? Anyone know what the voltage across the light bulb would be? What's the voltage across any outlet, any light fixture? Can someone tell me? Anyone? So when you plug something into the wall, what voltage does the wall provide? Anyone? Gosh, I thought this was common knowledge.
Just throw a number out. Would it be 12 volts?
No, that's what you get from a car battery.
Okay, that's what I'm thinking.
Yeah, 12 volts is what you get from a car battery. That's pretty standard though. And for household wiring, it's different. Who was that?
Jacob Horsley?
So for household wiring, anyone? Does anyone know? Anything on chat?
Yep.
Okay, it's 120 volts.
Yeah, we had one right when you said what it was, 120.
Who said that?
Crystal Chase.
Okay, Crystal, you are right. It's 120 volts. But it's 120 volts alternating current. And let's see, guys, could you get ready to turn off the lights? What I have here is a little LED, a light emitting diode. And when electricity goes through it, the light turns green. But if the electricity goes the other way through it, the light turns red. And so we're going to power this with straight AC power from the wall. And so the question is, what color is the light bulb? Is it red or green or what? Anyone? I don't think we need all the lights off.
Oh, you don't need all the lights.
Yeah. Yeah, that's probably good as well.
That's good.
That's good. Good. So what color is the light bulb? Anyone? Is it showing up okay on screen? I'm not quite sure.
I don't know.
Isn't it red?
Sort of.
It looks red on camera.
Okay, let's go ahead and turn all the lights off. Maybe this will show up better on camera.
Yeah, it's actually working fairly well.
Okay, is that showing up
Yeah.
on camera okay?
Yeah.
It's really clear in the classroom. Can you see it flashing? Folks in the room here?
Yeah.
Okay, it's red and green. So the electricity company sends us some electricity, the light turns green. But then they take it back, the light turns red. And look, in between, they turn off the power. Are you getting a fair deal from the electric company? Go and turn the lights back on. Anyone? Yes, we are. Because as long as there's charge moving, there's energy there we can tap into. So for reasons I'll discuss a little bit later, we use alternating current for our household power, as well as pretty much our whole power grid uses alternating current, AC power. But as long as the average voltage is 120 volts, that's all that's important. It doesn't matter which way the electricity goes through a light bulb, it'll still turn on. So What resistance do we have? Well, we know we've got 40 watts. So our power is voltage squared divided by resistance. So resistance will be voltage squared divided by power, or 120 volts squared divided by 40 watts. And that comes out to 578 ohms. So that is the resistance in ohms of a standard 40-watt light bulb. Okay, so here's what I have. This is kind of like what we did in class. I've got 120 volts across 3 40-watt light bulbs. And you can see that they're all equal brightness and not very bright. The circuit down below, if you can look at it, electricity goes along this wire and then back along this wire, but we have the wires for each bulb going between these 2 parallel wires. This is called a circuit in parallel. And if I were to draw a symbol for that, I would have our voltage source. And I would have a connection like this. And you notice that each light bulb is brighter. That's because the voltage across each light bulb is the same as what it is across the battery. So when we do it like this, each light bulb we say these two are series circuits. This is a parallel circuit, in that all the circuit elements have the same voltage across them. And I'm going to write that as delta V, or voltage change. The voltage from one side of the resistor to the other is the same. So if this was 120 volts, like what I have here, the voltage drop across each resistor would be 120 volts. And so if the resistance is about 578 ohms, well, let's just conveniently round that up to 600 ohms. So that would mean the current would be 120 volts divided by 600 ohms. So what's 120 divided by 600? Anyone? That would be around 0.2, or a fifth of an amp, about 0.2 amps. That's rounding up, but so it's going to be on the order of tenths of amps through each light bulb. And so if we have a certain current through each light bulb, that means the total current coming into and out of the battery is going to be 3 times that. So if we have 0.2 amps going through each light bulb, the battery is going to produce 0.6 amps. And that if we basically look at any junction, the current going into that junction will equal the current going out of it. So if we have I current going this direction, we're going to have 2I current going this direction. So 3I going in, 3I going out. So if 0.2 amps goes through the resistor, that means 0.4 amps are going farther down the circuit. And so at the next branch, the next fork in the path, we'll have 0.2 amps going straight and then 0.2 amps going down. So that we'll have 0.2 amps going through each circuit element. But with the voltage across each of these light bulbs being 120 volts, you can see they're very, very bright. This is like as bright as the single light bulb you had connected up to your battery when we did the activity. Contrast that to when we have them in series. Now we have 120 volts, say between here and here. That means there's a 40 volt drop across each light bulb. So basically we have 3 times the current in this situation than we do over here, because we have less of a voltage drop, basically a third of a voltage drop across each light bulb. So it's all a matter of proportion. Okay, now let's go to that slide that I had, the PowerPoint slide. Ooh, we need the projector on. While we're waiting for that to warm up, any questions on this whole circuit idea? So in your house, do all the other lights dim when you turn one light on? No, they don't. That's because all the circuit, all of the outlets, all of the lamp fixtures in your house are wired in parallel, so that every outlet has 120 volts across it. Every light fixture in the ceiling has 120 volts across it. And so when you flip a switch, what you change is how much voltage is being drawn from the power grid. Sorry, how much current is being drawn from the power grid. The voltage that's provided to your house is constant, and the voltage across any given outlet is also constant. You'll have outlets with 120 volts, that's almost all of them. All of your light fixtures will be 120 volts. But around your dryer, you might have a 240 volt plug. It's wired differently. And if you've got a machine shop, you might have a special wiring so that you've got a 440 volt outlet. But for most homes, you either only have 120 volts or 240. And the 240 is where you have your dryer. And so all the wiring you have in your house is done in parallel. Series is not something you see very often. You used to see it in Christmas lights. If a bulb goes out on an old Christmas light string, what happens to all the lights on the string? Anyone? They either all go out or a large section goes out, because you've got either all the light bulbs, all little LEDs, all little bulbs. In fact, the old ones had little incandescent bulbs, teeny incandescent bulbs. They gave off a lot of heat. If one went out, they all went out because they were in series. And that if one burned out, that stopped the flow of electricity, and no electricity would go through the others. But if you've got a Christmas light that's in parallel, where you have all the voltage across 31, if one burns out, that really doesn't change anything. It only changes how much total current is being drawn by that string of lights. Okay, so let's consider the situation. In fact, I've got that wired up over here. I have 3 light bulbs that are in series. And if I flip this switch here, I will make a connection between the wires here and here. Just like what I have there, if I throw the switch, I will create a path for electricity down here instead of through this light bulb. When you throw that switch, what will happen to the brightness of the light bulbs? There's 6 possibilities here. All 3 will dim. Only bulb C will dim. Or A and B will get brighter and C will dim. Or C will get brighter and A and B will dim. Or A and B get brighter and C will turn off. or the brightness, in fact, will not change if I throw the switch. So I'd like you to think about this question for a bit. What's going to happen? When you have an idea, get your folder out and choose the card. I kind of use the folks here as kind of an idea of how long people need to think about this. Okay, show me your cards. Can we move the chat thing so we can see what's up there? Okay, what do we have on the chat?
Looks like one E and the rest are all Fs.
One E and Fs, okay? In class, we have Ds. So it looks like we have folks choosing D, E, or F. Well, I'm going to say right off the bat that it's not A, B, or C. Let's just eliminate that. It's either D, E, or F. Could I get a volunteer to defend why D is correct?
I chose B because, like you showed us over there with that flashlight, that when you have them in parallel, they shine brighter, and on the when they're in series, they get dim.
Okay, Miss Murrow, right? Okay, so what Miss Murrow said is that when flipping a switch, it's like we're making bulb C in parallel. And in parallel, the light bulbs were all brighter. And so with the circuit being more parallel, where C is, that should make that bulb brighter. But A and B should get dimmer because that's taking electricity away. Is that kind of what you're thinking?
Yeah.
Okay, can I get a volunteer to defend E? That A and B will get brighter and C will turn off.
I can.
Please do.
The reason I did that one was because that would give it a route where it doesn't really need to do CN. With most things where resistance is provided and there's flow, it'll go along the path of least resistance, which makes me think that it would probably just avoid C entirely and just go straight back to the battery.
Okay, so what Ms. Barendisser was saying is by throwing the switch, we're shorting out bulb C. We're providing a path of less resistance, and so all the current will go through the switch, and no current will then go through bulb C. So it's going to turn off. And why would A and B get brighter?
Well, because that puts less bulbs in series.
Okay, so we have the same voltage across two bulbs that we had across three, and so this would be like the two bulbs that we had as opposed to the three bulbs in our activity. We just should expect two bulbs to be brighter than what we'd have with three bulbs. Okay, can I get someone to volunteer why F is correct in that the brightness shouldn't change at all?
I can give it a shot.
Please do.
I just kind of related it to both of our activities that we've done last Friday and Monday, how every time in my group we connected things, they all lit up the same. So the brightness never changed.
Okay, so in the activity, you had no change in brightness, no matter how you connected it up?
Yep.
Okay. So let's talk about this. Have some discussion. What's going on here? I didn't do it. Okay, anything showing up on chat?
Crystal Shice thought it was F because it's a series circuit.
Okay. Is that the only chat?
Yeah, nothing else so far. Okay, we got one more from Alexis Boomer. I can see how E could be plausible due to the answer made, but still see F more correct due to it being a series circuit.
Okay, I think we've had enough time to think about this. Any other chats?
No more chats so far.
Okay, go ahead and show me your cards. Folks, hit the chat buttons. What do you think is going on?
No change on chat.
So, but you do have entries?
It's all F and 1E.
Aha, so basically all Fs and one E?
Mhm.
Okay, we have no more Ds then. We have all Fs except for one E. Thankfully, science is not a democracy. It is a dictatorship dictated by experiment. So let's flip the switch here. Let's see what happens. Here we have 3 bulbs in series, kind of like what you had in the activity. When we flip this switch, we're basically providing connection where the current can bypass the one light bulb. On this diagram right here on the blackboard, that's like putting a wire right here. The current that comes out of the second light bulb has a choice. Does it go through this light bulb over here where the resistance is large? Or does it go this way where the resistance is 0? Well, the answer is clear. Electricity takes the path of least resistance. You're always going to have more current going through whatever path has less electrical resistance. And if it has no resistance, that's where all the current's going to go. But technically, it's not all of the current. These light bulbs, again, a 40-watt light bulb has a resistance on the order of 600 ohms, 578 to be exact. The resistance of about that much of bare wire is on the order of 1/1000th of an ohm. So there is current going through this, but it's about 10,000 times less than the current going through the straight wire. And so if we have, a couple of amps going through these light bulbs, we're going to have about on the order of 1/10,000th of an amp. So we're talking microamps through this other light bulb. That amount of current's not enough to make that little wire glow. So technically there's a teeny amount of light going through this by about a factor of 10,000, but very little. So what we have here is these 2 bulbs are still in series with each other with the battery, but this guy's completely shorted out. That's what we mean by short circuiting. We completely eliminate this from the circuit because the electricity is just not going to go that way at all because this has resistance. Basically, if you've got like 2 pipes, one is full of gravel and the other one isn't, you're not going to get any water going through the one with gravel. It's all going to go straight through the pipe that's clean. Okay. And Okay, that's probably good for them. So that's about all I wanted to say about this, this chapter. I'd like to move on and talk about magnetism. And let's go ahead and go to the next slide if we could, please. So if we have a negatively charged rod, move the cursor over the negatively charged rod. It's this guy right there. That's a negatively charged rod. And there's an insulating ball, and it's attracted to it. And then we have the same ball. We do nothing to it, but then we bring a positively charged rod near it. That ball is pushed away. What would happen if we brought the north end of a bar magnet towards that same ball? That's the question. Would the ball be attracted to the magnet? Would it be repelled, or would it not be affected by the magnet? That's the question. Okay, go ahead and show me your cards. Hit letters on chat, please. A, B, or C. Okay, what do we have on chat?
Mainly A's and one B.
Okay, but no C's?
No C's.
Okay, can I get a volunteer to defend why A is correct?
If no one else is going to, I can.
Okay, go ahead.
So this is a little bit of loose logic, just kind of based on our conventions around this. In most magnet kits I see, usually the north end is colored blue, which is the same as color that in a lot of things we tend to associate with the negative of charge. So I'm assuming that means it has a negative charge, which means it would have the same reaction as the negatively charged rod, being attracted to it.
I can't use them. Okay. Could I get a volunteer then to defend B, please?
I put down B just because I knew C was not the right answer, so I figured I had a 50-50 shot.
Okay. Anything besides that? Who's this?
Crystal, she's.
Okay, does anyone have anything to add to either point? Well, discussion here is a little bit pointless because no one chose the correct answer, which is C. Basically, let me go into a little bit of history here. The Greeks were the first to record the results of their experiments with magnets. Other cultures, I'm sure, played around with this, but the Greeks had an advantage in that there is a portion of Greece, which is now part of Turkey, called Magnesia, where you have very naturally very strong magnetic ore deposits, a lot of what's called magnetite. So they were blessed with having a lot of very noticeable magnetic rocks around. And so they played around with magnetism. And they found no connection between electricity and magnetism, in that something that was magnetic had no effect on electric charges, and something that had electric charge had no effect on something magnetic. The convention was that there was absolutely no connection between electricity and magnetism for a long time. In fact, that persisted until the early 1800s, when folks were rather astounded by the discovery of a physics teacher during class. He noticed something rather strange. I'll get into that in a little bit. But in general, electric charges, static electric charges, are not affected in any way whatsoever by magnetic fields. Now, let me put a caveat on this. That should be. I just can't have, I have to have them separate. You can't have them in strings. And then if we look at this, we know that something neutral will always be attracted towards something charged. The fact that this ball was pushed away by the positive charge rod tells you that that pith ball is charged positive. And so that positive charge ball should be attracted towards anything neutral, including the magnet, especially if the magnet is made of metal, which most permanent magnets are. And so you should see a slight attraction to it. So you could argue that A, in fact, is correct, but really not for the reasons stated. And I think we're kind of getting off track. But let me tell you a little bit more about Oersted's discovery. And for this, we're going to need to have a pretty good, this is pretty small.
You can use the document camera.
Do you have it set up?
It shouldn't take, actually, no, it is off, so it's going to take a bit to warm up. Never mind, we'll just use my laptop.
Okay, so what I have here is I've got a compass needle, and I've got some wire that's nearby. So let's see. Yeah, we have it up there. If I put it here, is it noticeable? No, let's put it on something. How about here? Is it showing up on the white background? Okay, so it is showing up a bit better on the white background. So what Oersted noticed is that one day he was doing some demonstrations for his class on magnetism. So he had some bar magnets, compasses lying around. And the next day he wanted to talk about electricity. So on that day he had some wire and he had some batteries and he was going to hook up some circuits. But he had some compass needles right next to the wires that he was hooking up, and he saw something rather funky happen. Watch what happens when I connect up this battery to this wire to get electricity going through this wire. You see the compass needle flip? And if I turn the battery around and make the electricity go the other way, the compass needle flips the other direction. So this is kind of what you saw in the activity that we did yesterday. Electric currents produce a magnetic field that can deflect a compass. This told us that there is a connection between electricity and magnetism. Furthermore, this showed us where magnetism comes from. It was the first clue into the actual origin of magnetism. So what I have here is I have just a regular bar magnet, and if I put a piece of paper over this, for this you want to get close to a vertical view. If I put some little slivers of metal here, filings, you can see they line up along, they make a pattern. We've got the north end over here, we've got the south end over here. The little pieces of metal line up along lines that go from north to south. We talk about the north end being a source of magnetic field and the south end being like a sink of magnetic field. Kind of like a positive charge is a source of electric field and a negative charge is a sink for electric field. But in between, the magnetic field goes from south to north. So the magnetic fields traced out here are actually like the capital letter D. And not just in the plane of the paper, we've got magnetic field going up, down, and then straight back. So inside a magnet, the magnetic field goes from south to north. Outside the magnetic field goes from north to south. There is no beginning or end to magnetic field. So it's really not a source. We just think of the north end as where the magnetic field leaves, and the south end is where the magnetic field enters. But it doesn't stop, so it's not like electricity. You cannot separate the north and south pole of a magnet. If you break a magnet in half, you don't get a north end and a south end, you get two poles, two magnets, each with the north and south pole. So if I broke this magnet in half, the part on the right would have a north pole and then a south pole right here, and the part on the left would have a north pole, south pole right here. So when you break it, you'd suddenly form two new poles. And this will continue even down to individual molecules. And the Greeks, didn't really have the best handle on molecules, but they knew that if you broke a magnet in smaller and smaller pieces, you can never separate those poles. It was for that reason, more than anything else, that they felt that there had to be no connection whatsoever between electricity and magnetism, because there's no such thing as a magnetic charge. The Greeks were convinced of this. And even now, we've never found a magnetic charge. But this discovery of Oersted gave us a clue of where magnetism comes from. It comes from moving electric charges. In the all magnetic field is due to the motion of electric charge. Even in a permanent magnet like this one, every atom is magnetic because inside every atom you have electric charges that are moving. And most of the time, this motion of electric charge doesn't produce a magnetic field. But in some materials like iron and nickel and cobalt, we do have, well, actually almost every atom is magnetic, but the magnetic fields of atoms are in random directions in most solids, so they cancel out, we don't notice it. But in magnetic materials, through a quirk of quantum mechanics, they actually like to align their magnetic fields to their neighbors. And so we can magnetize them by making more and more neighbors going in the same direction. Normally, a magnet is divided up into small, what we call domains, where in each teeny chunk, about a micron across, you've got all the atoms with a magnetic field in the same direction. And then in a nearby domain, yeah, their magnetic fields of the moments of all the atoms are aligned, but they're in a different direction. So that overall, there's no net magnetic field, because producing a net magnetic field is a high energy state. And energy tends to be minimized. Basically, there's more configurations for the magnetic fields to be in different directions across different domains. And that's, again, where thermodynamic statistics come in. But we can magnetize magnetic materials by putting huge amounts of energy into it and forcing domains that have a magnetic field in one direction grow at the expenses of others to get a very strong magnet. And so that's what we see in magnetic materials. So even in permanent magnets, it's the motion of electric charges that produce that magnetic field. And we can do lots of cool stuff with this. You can make your own electromagnets that are pretty simple. You just take a wire and wrap it around a nail. And this isn't doing much with little pieces of metal. But if I send electricity through this wire, I can produce a magnetic field that can magnetize the nail and turn this into a fairly strong magnet. I think this battery is about dead. I was expecting more. Okay. And we could use, here I have 4 batteries connected to a bolt with more wire. This should be even better. Let's see, can I use a small guy to lift up paper clips? Maybe I can get a couple paper clips. But that's about it. With this guy, though, yeah, I can pick up quite a bit more. This is more batteries, more voltage, more current, and more wraps of the wire. Now remember, we saw a deflection of the compass needle that was perpendicular to a wire carrying current. That's because the electrical current, the magnetic field produced by the current is in the form of loops. Just like in the bar magnet, we have loops going from the north end to the south end and then back. Magnetic field is always loopy. So if we have electrical current going, say, up the wire here, the magnetic field is going to be in the form of circular loops, rings around the wire. Out here, the magnetic field is weak because it's far from the wire. Right up close, it's going to be stronger. you saw this yesterday when you brought the wires near the compass needle. You had to get it pretty close for you to see an effect. So the magnetic field is loopy. We can actually increase the magnetic field strength by looping the wire. So with the wire looped, the magnetic field is going to curl around the way my finger curls. And so we can have the current over here on this side of the loop and the current over here on this side of the loop, producing a magnetic field in the same direction. So it's going to add in the center of the loop. And by making the loop smaller, we can make the field right in the center of the loop stronger. And we can double the strength of that field by having 2 loops. We can triple it by having 3 loops. So the more loops we add, the stronger the magnetic field is going to be in the center, because the magnetic field produced by any little bit of current in a wire is always a circular loop. So by looping the wires, we make the magnetic field much, much stronger in the middle. That's why I wrap the wire around the compass like this. We get a much stronger effect than what you were able to see yesterday. And that's also why the wire is wrapped around the nail. It doesn't have to be very pretty, as long as it's just wrapped in the same direction. The magnetic field right there in the center of those loops is going to be in the same direction and quite strong enough to magnetize a nail. So you can make your own electromagnets like this. Kind of fun. And we can do a whole lot of really cool ideas with this, but I was hoping for a bit more, but let's see. The folks here today, is this? Okay, good. I've got here several thousand loops of wire in this ring. Here I've got maybe 20 or 30. Here I had about 10 loops. So the more loops of wire, the stronger the current, the stronger the magnetic field. So my question is, are you 2 folks stronger than a flashlight battery? Would you be willing to do a tug of war? Mr. Navarro? Did I say it right? Navarro, okay. So right now, there's not much of a traction. So if I flip it, go ahead and try not to, well, just try to pull, but don't pull to the point where you'll fall over. I'm actually surprised. You shouldn't be able to do this. Wow. This is like ridiculously weak. It shouldn't be that easy.
Battery might have gone out. I'll grab a new one.
Well, let's try this one. I know this battery isn't doing so well. It might also be a short somewhere. No, that's even worse. Yeah, I think there wasn't a very good connection. I think I've got a better connection this time. No, maybe not. Oh, well. But the strongest magnets we can make are electromagnets, kind of like this. There might just be a short somewhere that we don't have all the current going through all the wires. Yeah, that's the problem. This is just really, really weird. So yeah, there might be a leakage current in the switch.
Okay.
I'll
take a look at it.
Okay. Okay, but we could do some other cool stuff with this, but I think we're out of time. So we'll continue with this discussion tomorrow. Thank you for your attention. Got a lot of really cool demos for tomorrow.